Okay, and for problem 3, we have the capacity of a building to withstand earthquake forces without damage, having a normal distribution with a mean of 2,500 tons and a coefficient of variation of 35%. If the building has survived a previous earthquake with a force of 1,500 tons without damage, what is the probability that it can withstand an earthquake with a force of 3,000 tons? So let's start with that. Let's go over here. So we have we're looking for the conditional probability because it does say that it has withstood an earthquake of 1,500. So we're looking for the probability of being greater than 3,000 given that it's 1,500. So by the definition, we have the intersection here between greater than 3,000 and greater than 1,500, which translates to 3,000 divided by, so as we did in 1b, we can express these as the complement, and then we can just use phi. So because it's a normal distribution, so we have 3,000 minus 2,500 divided by 0.35 times, which is the definition of the coefficient of variation. And same thing here, we have 1,500 minus 2,500 divided by 0.35 times 2,500. So by the lookup tables and some simple calculations, we will end up with a probability of 0.326. Okay, so moving on to the more interesting part of the question. Occurrences of the earthquake with a force of 2,000 tons can be modeled as a Poisson process with an expected occurrence rate of once every 20 years. What is the probability that there will be no damage to the building over 50 years? And this is where it gets a little tricky because we're not only looking for the occurrence of that particular earthquake, but we're looking for the occurrence of that earthquake causing damages. So if you remember from the problem we solved either with the overloaded trucks in the Poisson process or even some of the homework problems where we're looking at the fatal accidents instead of just the accident, we're doing the same exact thing here. So if we consider the random variable being the damages, the occurrence of damages in the 50 years, we have a Poisson process. So let me switch over to here, this note. Let's see. Okay, there we go. Okay, so we have the probability of no damages following the Poisson. So we have e to the minus lambda t raised to the 0 power, and then 0 factorial here. So that will get us to this probability. And now the question is, how do we find lambda and t? So t is easy, that's 50 years. That's our period. Lambda, though, now we're getting the damaging earthquakes, the occurrence of damaging earthquakes. So that would be the product of the mean occurrence rate, right? So we would have 1 over 20. And here we're looking for the probability that we have the x from our previous question being less than 2,000. So if the capacity is less than 2,000, then that means that the earthquake actually did cause damages, right? So now for this, because we know that it's normally distributed, we have 1 over 20 times phi, 2,000 minus 2,500 divided by 0.35 times 2,500. And with this, we can finally get probability of 14 after it's multiplied by the occurrence rate of 1/20th. So this 0.014 is the mean occurrence rate of damaging earthquakes for a building that has a capacity to withstand an earthquake of 2,000 tons. Or less than 2,000 tons, of course, if the earthquake is of that magnitude. So now that we know lambda, we know t, we can just put everything in this equation. So we have minus 50 times 0.014. So that will get us to 0.491. All right, and the last question, which was, in a complex of 5 similar buildings, each with the same earthquake-resistant capacity as described above, what is the probability that at least 4 of them will not be damaged under an earthquake force of 2,000 tons? Assume that the occurrence of damage to the different buildings are statistically independent. So let's go back here. So now we have binomial distribution, right? Because we have a certain number of trials, the 5 buildings, and we're looking for occurrences. So if we're looking for at least 4 of them not being damaged, that means that at most 1 of them is going to be damaged. So if we have the probability, the random variable rather, of B being the number of buildings damaged, what we're looking for is the probability that B is less than or equal to 1. So at most 1 will be damaged, so that means that at least 4 of them won't be damaged. So we're using the PMF rather, for the binomial. So we have 5, and then 0. So that's the case of B equals 0, and then we're going to have the case of B equals 1. And we're going to add them because, again, we're looking for the CDF. So let me just write the equivalent terms at the same time. So now we are looking for the probability of occurrence, so damage. So the probability for a single building being damaged, we saw that it is coming from this, right? And calculating that from a previous step, we have 0.284, and raise it to the 0 power, and then we have 1 minus 0.284, 5 minus 0, and same thing here, 1 minus 0.284, 5 minus 1. So we know everything, we plug everything in, and we should end up with a probability of 0.561.